As we wrap up the EIGRP world, it's time to focus in on some best practices and design options. EIGRP is one of those protocols that is very simple to configure. In that is one of its greatest weaknesses because people can set it up and not really have a good idea of a network design, and EIGRP can end up eating their network alive. I say that because of one message, and that is the query message. We're going to take a look in this nugget at number one, looking into the neighbor relationships, as in how are these neighbor relationships communicating, what messages are being sent, and we'll eavesdrop on those EIGRP neighbors to see just how often those messages are coming across. One of the big messages we're going to focus on is the query message, which can eat your network alive if you have a poor design in place. So we'll take a look at how to make EIGRP more efficient, not only by bounding those queries, that's one of the terms you'll get used to, but also to implement features such as Graceful Shutdown to allow your routers to notify everybody when they are going down. The first thing I want to do is eavesdrop on some EIGRP neighbors. It's a very busy neighborhood in the EIGRP world. And if you ever want to know what's going on, all you need to do is do a debug of EIGRP and just look at the packets. Now, if you want to focus in on a specific neighbor, and maybe you have many neighbors, then you can just focus in on that. But debugging EIGRP packets will give you kind of a tap into all of the communication happening between the EIGRP neighbors. Now, I've got to warn you, when you hit enter, which I'll do, it's going to debug everything. You can see all the different packet types that are going to be sent by the EIGRP peers. And since this router does have quite a few interfaces, you can see it's sending a ton of hellos. Hello, hello, hello. It's going out. I don't know if you can catch those scrolling by. They're going out the loopback, the serial interfaces. I can't even highlight them fast enough. Hang on. Freeze. Right here we can see that we've got the what was I talking about? Oh, the hello messages. You can see it going out the serial 0/0, and I can't move. Oh, maybe I can move my mouse this way. Serial 0/0.3 to a neighbor over here. It's also sending them out even loopback IP addresses, and of course it's saying packets from ourself are ignored. So it's just saying, hey, I sent one, I ignored it. I sent one, I ignored it, because a loopback comes back to itself. So quite a few packets will be displayed when you do that. So let me do a U-all and turn off all the debugs, because a more efficient way to go about it, it's one thing to check the hello packets, but you can type in debug EIGRP packets and then focus in on what you want to see. I like it because you can type in one right after another of the packets you want to find. For example, when a network goes down, the router should send a query message to find out, is there another path to this? And the other routers should send a reply message back. So I can type in, I want to see query and reply packets, and hit enter without the fear of just being swamped by a ton of packets. So it says the debugging is on, query and reply. Now let me do a show IP interface brief, because you can see I've actually added a network since the previous video. This one right here, 172.30.8.1 on the Ethernet 0/0, which you can see is currently up. Now I've got a secret that's not plugged into anything. The way that it looks like it's up is because I turned off the keep alives on the interfaces. So what I'm going to do is turn those keep alives back on, and we should see it detect, hey, there's nothing plugged in, the protocol will go down, and look at it, look at what happens now. Protocol just went down, and immediately it sends out a query to every single one of its neighbors. You can see it's in queuing. That means it's queuing up, getting ready to send it, and then it sends it, in queues for the specific neighbors right here. Then it sends the queries to those neighbors, and they immediately reply saying, sorry, you're out of luck because that is your Ethernet 0 interface. We don't have backup connections to that. So you can see how trimmed down the debug is when you just focus it in on the packets that you want to see. Now, the query packets, the reason I debug the queries and replies is because that's one of the big things I want to talk about here. EIGRP routers use query messages to find backup routes around the network. Now, you might remember back to the EIGRP concepts video, I talked about one of the unique features of the EIGRP protocol in that it was one of the only protocols that kept backup routes. So if the primary went down, it can immediately switch over to the backup routes. But remember, there were requirements for that. Like, let's say I had an EIGRP router here with 2 paths to reach the same network. And I think this was the exact diagram I used back in that concepts video. I said, well, if the advertised distance, remember what we'll say router 2 thinks it is to reach that network, if it's less than the feasible distance of the primary route, which maybe is that way, then it will be considered a backup route. And we talked about it back then. I said that's a loop prevention mechanism, and I don't want to get into all the detail. But one of the points that I brought out was that if this is like a horrible route, and in the sense that its advertised distance is not less than the feasible distance of the successor, it's not that it won't be used, it just won't be used as quickly, as in it needs to use query messages to rediscover that route should the primary route goes down. So if this goes down, the router can send a query message saying, hey, do you have a backup path to the 10.1 network, which we'll say is down here. And this router will respond and say, why, yes, I do, and then it will use this path, which takes a little longer than the backup method, but it will still get there. Now, the query messages are a good design because it allows the router to discover the backup routes around the network. However, the query messages can also destroy you. Watch this. We have right here kind of a, I guess you could call it a corporate network, where the corporate network begins right here with these 2 routers, and maybe you have a primary router and a backup router that allows you to reach the same networks. Now, whenever a network goes down in EIGRP, query messages are the natural response. So let's say on router 2 right here, it loses the 172.30.1 network. As soon as that goes down, it will immediately send query messages out all of its interfaces, all of its active interfaces, to the neighbors that are on those interfaces to see if they have a backup route. Now, I know you and I are looking at that topology right now going, what are you thinking? You know, router 2, come on. You're the only connection right here to the 172.30. But router 2 doesn't know that. It has a connection, but who knows? Maybe this router over here has a connection to that network somehow. It might want to use that one as a backup. So the way the query messages go is they will go to every neighbor on an active interface except for the interface where the failure occurred. Of course, it won't send a query message out there. Now, query messages, when they're received by the routers, if they do not have information about that network, then they'll pass it to their neighbors. So here's where the chaos begins. Let's just follow this one query right here. It bops up and hits this guy. He doesn't have a connection to that network, so it sends it to all his active neighbors, which are 1, 2, 3 messages out to these neighbors. Now, I have houses pictured there, but they could very well be branch offices, telecommuters, who knows. They get the query messages. Let's pick on this guy. He says, oh, I don't have a connection, so I'll send it to all the neighbors on interfaces where I didn't get the query message. So the query message comes in here. There's no sense in asking that guy about it again. That's part of split horizon. So it sends the query message out here to this neighbor, who gets it and sends it over here to these neighbors. So you can see that the query message madness can swarm this network with even 5 routers. All of these routers will get the queries and send the queries and just kind of start this network storm of all these queries where you kind of have all this chaos happening, processors escalating for a network that only router 2 could reach anyway. Now, one of the things that I want to bring up here is that, let's say, just by chance, this router did have a connection to that network somehow. When router 2 sent out the query messages, before it can make a decision, it has to hear back from all the queries. So let's say, again, this network goes down, but this one did have a backup path to that network somehow. Maybe ISDN, maybe Direct Connect, who knows. The query messages would all go out, and that storm would start all over. This router would respond and say, yes, I do have a backup path to that. And router 2 would go, oh, great, I've got a backup path, but I'm not going to use it until I hear back from all of these neighbors. Okay. It will wait, by default, 3 minutes to hear back from all the queries. Now, this is a very small network that we have pictured on the screen. I mean, imagine these offices connecting off to other offices and, a network that maybe goes 10 in depth on all the routers swarming all around the network. Well, those query messages are just going unbounded all around the world. This guy is just waiting to hear back from them before it can actively use that route. This is a symptom that they actually refer to as stuck inactive. After 3 minutes, that's where a stuck inactive state occurs, it will actually destroy all these neighbor connections. It will actually down the whole neighbor. Can you believe that? He'll say, hey, I guess I'm not hearing back from you, so it must be a neighbor problem. So it takes down the neighbor and reestablishes the neighbor relationship, and then everything is fine, hunky-dory. It can then use this route. But think of what just happened there in the stuck inactive state. When it went to stuck inactive, first off, every network went down from router 2's perspective, meaning it killed all the neighbors, and all the networks became temporarily inactive. Second thing that happened is router 2, within seconds, if that, of sending out the query messages, had an answer. There is a backup route. Come this way, Seymour. But router 2's like, no, I'm not going to use that route until I hear back. So you go into a state of 3 minutes minimum of downtime before router 2 even reacts to the success message. So, all in all, with all this query madness that you see on the screen, I'm going to clear that off. There are 2 ways that Cisco has created to solve the query problem. Number 1 is a summary route. We can use summary routes to fix this problem. Number 2 is a stub configuration. Let's talk about each one of those. One of the big topics of the previous video was how to work with summary routes on an EIGRP router. By default, summarization is turned on with that auto summary command, so it will summarize back to the classful boundary, or we can turn it off and put in manual summary routes wherever we want. So let's say that this router down here, just for the argument's sake, we're going to imagine that it has all of the 172.30 networks from 1 all the way to 7, just like we talked about in the previous video. And we put that summary address on there. We did an IP summary address under the interface to let all of the other neighbors know I have everything starting with 172.16. I put 16 there. 172.30.0.0/21. That was the summary address we used. And so all of these routers summarized up the routing table that they had. All of those 8 routes from 0 through 7 got summed up into one summary address. It was great for the efficiency, but now you'll find out one other bonus. If one of these networks go down, and we'll say it's the 1 network again, the query messages will still go out to all of these routers, but here's the difference. When we send out the query message, the routers get it, and since they have a summary address saying, router 2, you have everything that starts with 172.30.0.0/21. Instead of forwarding the query on, they respond and simply say, no. So the query message is saying, do you have a backup route? Rather than saying, well, I don't, let me ask him, and let me ask him, and this thing just going all around the network, the routers respond with a simple, no, I don't, because you've told me that you have all of the addresses starting with that. So just putting in proper summarization is one of the ways that we can be efficient in how we advertise those networks out. So it's almost a moot point for me to talk about the stub configuration, even though it's very good. If you properly do summarization in your network, you won't have to worry about any of the query madness happening. The other alternative to summary routes is by using the stub configuration. In this picture, we have 3 stubs. This one, and this one. A stub is just a network that doesn't go anywhere. Think of it like a cul-de-sac in a neighborhood. You turn into the cul-de-sac, you see the houses there, but that's it. You got to turn around if you're going to go anywhere else. So these are the cul-de-sacs of our network. We don't have anywhere to go once we reach those. So if we configure these routers as stubs, what will happen is when the neighbor relationship is formed here, we'll say this router and this router form a neighbor relationship. In the neighbor negotiation process, it will come across to router 2 up here and say, hello, router 2, I am a stub. Pretty killer introduction if you think of that. And router 2 immediately realizes that since you have identified yourself as a stub, I know that the networks that you tell me about is the end of the road. That is your cul-de-sac. So I know that nothing else will be reachable through you except the stuff that you're telling me about. So when this network goes down, I won't even send a query to you. I guess that's one better than the summary routes, right? Because the summary routes, it still sent the query, it just got the no response coming back. With a stub configuration, router 2 already knows those are all stubs, so if the network goes down, why even ask them? They won't go anywhere. So when the network goes down, it will just come up here to this router saying, hey, do you have a backup route? It looks and says, oh, nope, and all my friends are configured as stubs, so again, I'll return the no answer back to you so you know what's going on. The stub configuration is a very simple config. Let me bring up the prompt right here into the screen. I'm on the backbone router. Let me just jump on over to router 2 so it's a little more logical. One of the spoke routers. And by the way, the stub is extremely useful in a hub and spoke style config, which this is. You can see these two routers represent the hub. These are all spoke networks, or the stub networks coming off of there. You just go under the router eigrp process and you type in the command eigrp stub, followed by what information you want to be able to advertise. Now you have a few options here. First off, by default, if you just hit the enter key after eigrp stub, the default is connected and summary. What that means is these stub routers that are in these little homes out here will just advertise whatever interfaces they have that are considered connected, and if you decide to configure a summary address on one of those interfaces, those will be advertised as well. So connected and summary are the default if you just hit enter. But maybe you don't want it to advertise summary routes. Then I could just type in eigrp stub connected and hit the enter key, and that's the only thing that will be advertised. If you really wanted this to be the ultimate stub, you could type in eigrp stub, whoops, I hit the enter key, eigrp stub, followed by the receive only. At that point, that's just as good as a passive interface is in the RIP world. In the RIP world, if you type in passive interface, that says I will receive updates, but I will not send anything. And when you type in stub receive only, that eigrp router says, I am a stub, I will receive updates, but I will not send anything. The passive interface command in eigrp does more damage than it does in RIP, because a passive interface will not form neighbor relationships at all. So don't confuse those two. If you use a passive interface with eigrp, that is effectively exempts an entire interface from the eigrp neighbor forming process. So that's the receive only. The only other alternative here you have is static. If you put static in here, the eigrp process will only advertise static routes that exist on the stub router. So maybe this router has a static route connecting it to some other network within the home. This router will possibly advertise those static routes out, but that is only if you do something known as redistribution, where you redistribute those static routes into the eigrp process. In all, what I would recommend is just typing in eigrp stub and hit the enter key. At that point, it does the default, which is connected and summary, which are the 90% of the time most often used statements that you'll have with eigrp. That will exempt these guys from the query process and make eigrp much more efficient. Okay, let me clear off the screen as we talk about the final topic I want to mention. And it's something that we've been seeing all along. Let me bring it up in the live configuration interface right here. You can see right here, look at that. It says a message, neighbor 10.1.24.2 is down because there is a k-value mismatch. Now, I don't know if you remember, when we talked back to the eigrp concepts, we talked about the 5 k-values, and they were bandwidth, delay, reliability, load, and MTU. They're all of the different things that can be used to calculate the metric of eigrp. By default, we only use k1 and k3 by setting it to a value of 1, which is the bandwidth and delay. So one of the things that I mentioned back in that video was that if the metric is different on the routers, meaning the K values are different, the neighbor relationship will not form. The neighbors will go down. So for instance, if this router right here is using bandwidth and delay, and this one is using bandwidth, delay, and MTU to calculate the metric, then these two can't be neighbors because they are using different K values to form that neighbor relationship. But that message then doesn't make sense because it comes up and says, hey, your neighbor right here is down because there's a K value mismatch. Well, but then right after that it says, oh, no, now the neighbor is up. And let's make sure. I'll do a Control-Z and do a show IP EIGRP neighbors. And sure enough, there's the neighbor. It's there. So either one of two things. Either one, somebody is behind the scenes changing the K values on those neighbors really fast. Or two, this message doesn't really mean what it says it means. And I can tell you the first one's not true because I control all those routers, so there's no mystery person unless I've been hacked in the background and the hacker is deciding to change K values. What we are actually encountering is a fairly new feature in the EIGRP world. When I say new, I mean in 12.3 release 2T. So not all that new, but fairly new. It's called a Graceful Shutdown. Before that release of the iOS, if a router went down because somebody reloaded it, or somebody did a clear IP EIGRP neighbors, or somebody did a shutdown on an interface that was connected to a neighbor, the router doesn't tell anybody. It just waits for that router's hold down timer to expire, which by default is 15 seconds on the faster interfaces. And the neighbor, when the hold down timer expires, it goes, oh no, the neighbor went down, query messages, let's find backup routes, switch over to the feasible successor. Whatever the case may be, it flips over to use the backup routes to reach that network. Now, unfortunately, that's not the most efficient process because at that point, if you did a reload on this router, it's been down for up to 10 to 15 seconds before this router detects it and does anything about it. So, in that release of the iOS, they released a new method of shutting down the process, and it's known as a Graceful Shutdown. Whenever you do anything that affects the EIGRP process, clear the neighbors, reload the routers, shut down an interface, the neighbor will send one final hello packet. It is a hello, but it sets all the K values to 255. Now remember, when you think back to the metrics, K1 and K3 were set to 1, but we could actually set it to any value that we wanted between 0 and 255 to have, for instance, bandwidth to have more effect on the metric calculation than delay, or, loading have more effect than the bandwidth. You could set those to different values. So Cisco said, well, we don't think anybody, well, we hope nobody would ever set all the K values to 255 because that is going to be a new reserved hello message. By doing that, that is known as a Graceful Shutdown. So when you reload this router, it sends out one final hello that bounces all the K values to something absurd. So this router immediately thinks, oh, the metric changed. That neighbor is now down. I can't form a neighbor relationship. On the older routers, it worked because it recognized it as a K value mismatch. On the newer routers that had an iOS of 12.3 release 2T or later, they didn't need to oh, sorry, this one right here. This guy is running a later and greater one. Notice he never said there was a K value mismatch because he recognized that as a goodbye message, as a Graceful Shutdown. It's actually known as a goodbye message. So this one, we'll say, had an old iOS. It said, whoa, K value mismatch. This one had a new iOS version, and if we were debugging on that one or just sitting on that console when the hello message was sent, you would not see it as a K value mismatch. It would actually say the message goodbye received because it recognizes that as a goodbye message. Regardless of the iOS version, the result is accomplished and the result is the same. Immediately, this one tries to find backup paths rather than waiting the 10 to 15 seconds that the typical hold down timer would result in. By using all of those features in conjunction, you can see that we can make EIGRP run much more efficient than the default. One of the best things that you can do for yourself is to do those route summarizations. By putting the route summarizations in the right place, you can be sure that the queries will be bound. So let's wrap things up. To hit the high points, we did first off an eavesdropping on the EIGRP neighbors. We did a couple debugs to see what messages were being sent, primarily hellos, but we can also see the queries and replies and all of those sorts of messages whenever there is a network in crisis. The second thing we did was to look deeper at those query messages to find just how far those things will go. They will go as far as it can, as long as it doesn't run into a route summarization or a stub network. So to bound those queries and thus make EIGRP more efficient, you can either put the manual route summarizations in place, or you can use the stub configuration so that the queries will never be sent in the first place. Finally, upgrading key routers to a modern iOS version, meaning since 12.3 release 2, is one of your best bets, because by doing that, adding the Graceful Shutdown feature can allow EIGRP to converge in a snap. I hope this has been informative for you, and I'd like to thank you for viewing.